Making observations is fundamental to all sciences. In chemistry, we record qualitative observations, but more often we make quantitative observations or measurements. A measurement always consists of two parts, a number and a scale or unit. Both of these elements are needed in order for the measurement to be meaningful. Scientists recognized a long time ago that a standard system of units had to be established if measurements were going to be useful. In the United States, we use the English system, but throughout the world, the metric system is used. Specifically in science, we use what's called the SI system, and it is based on the metric system and its units. In the table, there are some fundamental SI units you should be familiar with from your first-year chemistry course. We will be using these units as well as adding to this list in AP Chemistry. The fundamental units of the metric system are not always convenient. For example, measuring the volume of a chemical in liters isn't always the best way because it is such a large quantity. So we use prefixes from the metric system to change the size of the unit. You can see from the table that each prefix is based on a power of 10. We will be focused on many of the familiar prefixes you've used before, and maybe expanding on them a little in AP Chemistry. Now let's start making some measurement. If we consider the volume of liquid in the graduated cylinder on the screen, you may notice that the meniscus of the liquid occurs at about 21.3 milliliters. Since we had to estimate that last digit, it might be different if another person makes the same measurement. So let's say we had 4 people measure the volume of this liquid, 4 different people. You can see that the last digit of their measurement varies a little bit, but the first 2 digits remain the same. These digits that remain the same are called the certain digits, and the final digit, which is estimated, is called the uncertain digit. So again, just to clarify, certain digits remain the same no matter who is making the measurement, while uncertain digits can vary because they are estimated. When you are recording a measurement, you should include all of the certain digits plus one uncertain digit. Let's look at another example using a burette, which is another measuring tool used in chemistry. If we again read the volume at the bottom of the meniscus, it occurs at about 20.15 milliliters. Again, the 20.1 is certain because the tool is divided into the tenths place. The 5, though, is estimated, and so it is uncertain. Another individual might measure that at a 4, someone else may measure it at a 6. Any measurement always has some degree of uncertainty. The level, though, is dependent on the precision of the device being used to make the measurement. So let's look at an example using 2 different tools. A person was analyzing a sample of polluted water and measured out 25.00 milliliters of the water in the pipette on the right. Another point during the analysis, the chemist used the graduated cylinder to measure 25 milliliters of the solution. What is the difference between these 2 measurements? Even though the 2 volume measurements appear to be equal, they actually convey very different information. The quantity 25 milliliters, which was measured in the graduated cylinder, means the volume is somewhere between 24 and 26, where 25.00 means the volume is somewhere between 24.99 and 25.01. This means that the pipette measures volume with a greater precision and less uncertainty than the graduated cylinder. This brings us to a discussion of significant figures. When you're making a measurement, you need to record all of the certain digits plus one uncertain digit. These numbers are called the significant figures of the measurement. So if again we look at the burette on the left and measure at the meniscus, someone might say that that measurement is 22 milliliters. This would, however, be incorrect. The tool is divided into the ones place, so we must measure one digit past what we can see on the device. A more accurate measurement would be 21.9 milliliters, with the 9 being estimated. You may remember learning some rules for counting significant figures from your first year course. We're going to review those now and apply them also in AP Chemistry. The first rule is pretty easy. Any non-zero number always counts as a significant figure of measurement. For example, the measurement 34.56 has 4 significant figures. Where it gets a little bit tricky is with zeros. There are 3 different types of zeros. A leading zero, which would be at the front of a number, is not a significant figure. These are place-holding zeros. So for example, the first 3 zeros in this measurement do not count as sig figs, and only the 4 and the 8 are significant, and this measurement has 2 significant figures. The second type of zero is called a captive zero, or sometimes I call these sandwiched zeros because they're between 2 non-zero digits, and they are always significant. For example, in this measurement, 16.07, we can't measure the 6 and the 7 without measuring the 0 in between. So all 4 of these digits are significant, and the measurement has 4 sig figs. The final type of zero is called a trailing zero, and there are 2 types of trailing zeros. If the number does not contain a decimal point, then a 0 at the end of the number is not significant. If the number does contain a decimal point, any zeros at the end of the measurement are significant. So let's look at an example of each of these. 150, which contains a trailing 0 but no decimal point, means this 0 is not significant and the measurement only has 2 sig figs, the 1 and the 5. On the other hand, 9.30 has a trailing 0 and it also has a decimal point, which means this 0 is significant and all 3 digits are significant. Another thing to think about when counting significant figures are exact numbers. And these numbers have an infinite number of sig figs. So how do we have an exact number? One way is by counting. For example, if you do 10 trials in an experiment, or there's 8 atoms in a molecule, both of these numbers have infinite number of significant figures. The other instance is definitions. For example, 1 inch is known to be exactly 2.54 centimeters. So in this relationship, these numbers have an infinite number of significant figures. Let's look at some examples of using these rules to count significant figures. For the following measurement, a student extraction procedure of tea yields 0.0105 grams of caffeine, and we need to determine the number of sig figs in the measurement. The 2 leading zeros are not significant, but the 0 between the 1 and the 5 is significant. So this measurement contains 3 significant figures. A chemist records a mass of 0.050080 grams. Again, the leading zeros are not significant. The 2 zeros between the 5 and the 8 are significant, and the trailing 0 is also significant because the number contains a decimal point. So in total, this measurement contains 5 significant figures. And finally, in an experiment, a span of time is determined to be 8.050 times 10 to the negative third seconds. Both zeros are significant. The one is a captive 0 and the second is a trailing 0 in a number with a decimal. And the scientific notation does not affect the number of sig figs. So this measurement contains 4 significant figures. In addition to counting significant figures and measurements, when we do calculations, we need to report our answer to the correct number of significant figures. There are also rules for multiplication and division with sig figs and addition or subtraction. Let's start with multiplication and division. When you multiply or divide measurements, the number of sig figs in your answer should be the same as the measurement with the least number of sig figs used in the calculation. For example, if we were to multiply 4.56 by 1.4, the calculator would read 6.384. Our answer, though, is limited by the 1.4, which only has two significant figures. So we must round our answer to two significant figures, and it should correctly be reported as 6.4. Let's look at a division example. 1.05 times 10 to the negative third divided by 6.135. Again, the calculator gives the result on the screen. However, our answer is limited by the three significant figures in the first measurement. So we must round our answer to 1.71 times 10 to the negative fourth. Addition and subtraction is a little bit different. Instead of looking at the number of sig figs, we look at the number of decimal points reported in the measurements. And your answer should have the same number of decimal places as the least precise measurement in the calculation. If we were to add these three measurements together, the calculator would read 44.233. The first measurement was reported to the hundredths place, the second goes to the tenths place, and the final measurement is reported to the thousandths place. We are limited by the second measurement, and therefore our answer must be rounded to the tenths place. So the correct answer when adding these numbers is 44.2. A subtraction example, 21 minus 13.8 will give us 7.2 on our calculator. The first measurement is only measured to the ones place, and that limits our final answer. So we must round to the ones place, which would be an answer of 7. So note that for multiplication and division, we count the number of sig figs, and for addition and subtraction, we look at the number of decimal places. In most calculations, you are going to have to round to obtain the correct number of sig figs, so we should establish some rules for rounding. If there are a series of steps in a problem, you should carry the extra digits through to the final result and then round your final answer. When you are rounding, use only the first number to the right of the last sig fig. For example, if we need to round 4.348 grams per milliliter to two significant figures, we want to consider the number to the right of the second sig fig, which would be the 4. This would cause this number to round to 4.3 grams per milliliter. So when you are rounding, if the digit to be rounded is, or to be moved, is less than 5, then the preceding digit should stay the same. So if we're looking at 1.33, since that second 3 is below 5, it rounds to 1.3. If that number is equal or greater than 5, then the preceding digit should be increased by 1. So 1.36, since the 6 is greater than 5, this number would round to 1.4. Again, it's important to not round until your final answer. Let's look at a final example. As part of a lab assignment, someone was trying to determine the value of the gas constant R, and to do that they measured the pressure, volume, and temperature of a gas, and they have the mathematical relationship between these variables. The measurements are listed on your screen below, and we need to calculate R to the correct number of significant figures. So first, we're going to input the measurements into the mathematical model and then begin to solve for R. First, we multiply the numerator, and the result is 22.528. We don't want to round that just yet. And then we're going to divide that by the temperature to get the final result. Again, we are limited by the volume measurement, and so our final answer must be rounded to two significant figures, which would be 0.082. Now, let's see what would have happened if we had rounded each step of the way. So again, we input the values into the mathematical model. If we rounded that first step in the process to two significant figures, again based off of the volume, it would round to 23, and then divide by the temperature, we get the following result. Our final still needs to be rounded to two significant figures, which would yield 0.084. So I just wanted you to see that rounding each step is going to give a significantly different answer than carrying the extra digits and waiting to round at the end of your calculation.